All right, ready?
Size of atoms requires special microscopes to study their properties.
This microscope
Optical
will work.
microscopes don't have the required resolution. This deficiency is due to the use of light to image small structures. We use a scanning tunneling microscope instead. This microscope achieves its unsurpassed spatial resolution by exploiting the quantum physical phenomenon of tunneling of electrons. If the tip of the microscope is positioned very close to the sample, a current of electrons flows, which depends dramatically on the distance between tip and sample. Image acquisition via STM.
A scanning tunneling microscope.
The scanning tunneling microscope exploits this dependence of the tunnel current on the tip sample distance to obtain height profiles of the sample. To this end, the tip is scanned line by line over the surface of the sample, and the tunnel current is measured. If the scanning tip encounters a step on the surface, the tunnel current increases due to the smaller distance between tip and sample. A sequence of line scans provides an image of the topography of the sample. Imaging atoms. The high resolution can be used to image individual atoms in the surface plane of the sample. We resolved the atomic structure of a copper crystal. Our images revealed that the copper surface can be modeled as a close-packed arrangement of hard spheres, which are spaced at a distance of 0.22 nanometers.
So then the computer makes an image of what they think this would look like, and it looks like a bunch of hills, doesn't it?
Yeah.
So that's really one of the best pictures we have of what an atom looks like. These are copper atoms.
Imaging electron density variations. The atomic contrast resides on smoothly varying background. Typical modulation lengths are of the order of 1 nanometer, 5 times as long as atomic distances, and they're due to variations of the electron density within a surface. The tunnel current depends also on the electron density of the sample. Therefore, investigations of the electronic properties are possible. We study how the electron density varies due to electron scattering.
Last one. All right, last one.
Have you ever seen an atom?
Yeah.
Seeing as everything's made of them, you have. But have you ever seen one on its own? Over time, microscopes have become more and more powerful, allowing us to see deeper into the world of the ultra-small. Traditional light microscopes can be used to see things like these onion cells and the structures within them as they divide, pulling apart their chromosomes. But scientists have come up with a whole host of clever methods to observe far smaller things. Using beams of electrons instead of light, we can generate detailed images of chromosomes themselves.
This is just an electron
Recently,
microscope.
groups of scientists around the world are becoming able to see materials at the most
These are
fundamental
chromosomes,
scale.
DNA
the
and
atomic.
protein.
Exactly.
One group from the University of California in Los Angeles have been getting up close and personal with nanoparticles of platinum, just a few nanometers across. Each of the tiny dots you can see here are actually individual platinum atoms. But researchers didn't stop at a two-dimensional picture. By imaging over 100 slices of the nanoparticle at different angles, then removing the noise with a special filter, they were able to map the location of almost every atom. The information was used to create a three-dimensional reconstruction of the whole particle in unprecedented detail. It may look blurry, but this particle is estimated to contain over 27,000 atoms. And so, like flies in a swarm, they appear to merge together. Every so often, though, we see the platinum's atomic structure align, granting us a moment of clarity. This technique is being used to analyze tiny irregularities in the structure of the particle called dislocations. Dislocations are subtle, like the misalignment of the green and red layers of atoms in this particle. But nonetheless, they can significantly change the properties of materials, with effects ranging from a change in the efficiency of LEDs to the strength of metal alloys. Three-dimensional atomic scale imaging like this is bettering our understanding of the structure of materials on this truly fundamental scale.
All right, hold on. There we go. All right. So what I was going to do is, the reason I wanted to show you that to begin with is that I think a lot of you have this, and I did too, you have this idea that we're really smart that we actually know exactly what an atom looks like as if we have seen it. And we have all these other pictures. Have you seen pictures in like your book or in a book from middle school? Do you remember showing a drawing of an atom? And didn't you have like a nucleus and protons, neutrons, electrons? And you say, well, of course we've seen that. Why were they put in a science book if we have never seen it? Well, what I showed you, that's what we've actually seen. We haven't seen those drawings that are in the book. We haven't seen that. And then next question you would ask is, well, then how do we know? Well, that's a great question with science. There's a lot of things in science that we say we know because we've done experiments and say, this experiment leads us to believe this. It leads us to believe this. And so I want to ask you about what you know about the atom. Let's find your book here. Here it is. What do we know? I mean, how did we know this stuff? So let me show you a picture. Let me show you here. Right there, chapter 3, okay. Sorry, who did that chapter? Chapter 4. Okay. So what I'm going to show you in your book, this is the first page of the chapter. This chapter, there are parts to it. One of them is the history. What's the history? How do we know that atoms exist? How do we know their structure? And there's about 6 or 7 scientists in here that you'll want to make sure you know what they did. What did each scientist do? And I'll probably take a couple scientists every day and try to explain what they did. That's number one. Number two is we're going to go after the atomic structure. What is about the atom that I call the world of mass? What is about the mass of the atom, which is found almost exclusively in the nucleus? And then the other part is the charge of the atom, and that has to do with the nucleus and the electrons. And then we'll get into even the periodic table. Where are the metals? Where are the metals on the periodic table? Where are the non-metals? Why are they metals? What is it about the atomic structure that says you're going to act like a metal? And so we're going to be talking about that too. Anyway, let's take a look at this first paragraph. And every year I tell people that I don't know why this author writes the other book I even have for my advanced chemistry book. It's the same author. But I'm not sure why he left it out here. But this person's name is always in a chemistry book, except for this one. I asked people to go ahead and write in their book. You can write that. His name is Democritus. And Democritus, he wasn't really a scientist. You may be talking about around 300 BC. He wasn't really a scientist. So why is he in a chemistry book? So what happened back then, if you were in the Greek society, if you weren't going to war, a lot of culture, if you're going to war all the time, or if you're a nomadic kind of people where you're always moving, you don't have a whole lot of culture. You don't have time for it. But if you have periods of time where you're not constantly trying to fight somebody who's trying to kill you, you tend to develop culture. People start doing things like art, paintings and sculptures and books, and you get more culture. And so back then, the Greeks were very famous for having philosophers. What does that mean? What was a philosopher? A person who asks questions, isn't it? And they try to answer those questions. Even later, the word scientist didn't come about till, I don't know, late 1800s. They were called natural philosophers. They asked questions about nature and they tried to answer them. We call them scientists today. But there were philosophers back there, and Democritus was one. And they were probably sitting around and say, what do you think everything's made of? And I think every one of you should have asked that question sometime in your life. Sometime in your life, you should have said, what's everything made of? And so let me get a little piece of something out here. Try to find one. Here's one. So here's a piece of copper. Okay, here's a piece of copper. And I'm not saying they use copper, but maybe they were sitting around and saying, what do you think this is made of? And he said, I'm not sure. I'm not sure what it's made of. Well, let me ask this question. What happens if I cut it in half? What do you think if I cut this in half? Do you think this half will have the same properties as that half?
No.
What do you think?
Yes.
And some people said no,
I mean,
and some people say yes.
it'll have the same physical properties.
All right. They would be half the mass, but it would have mass, right? It would have half of it if I cut in half. Well, then they probably said, all right, so you think maybe it'll be the same? Oh, maybe. What if I cut them in half again? And again? And again? And again? And that's what philosophers did. They said, well, how far can we cut something in half and it's still going to act like this material? That was a great question. Well, there were a group of people that said, you know what? I think matter is infinite. I think you could go infinity. Cut it to infinity and it'll still be copper. And then some people like Democritus said, I'm not sure why, but I don't think so. I think that there's going to be a point where you cannot cut it in half anymore. And it'll be the smallest piece of copper you can have, but you can't cut it in half anymore. And they said matter was finite. Okay, so who's in the chemistry book now? I don't see the names of the people who thought matter was infinite. I've never seen their names. But Democritus is, because he thought matter was what? Finite. Another reason he's in chemistry books is that he used a word that meant indivisible, not dividable. And it was called atomos. And atomos was the name that meant non-dividable. And so why is he in chemistry books? Because what word do we use today? The atom. And so, anyway, it's kind of neat. It wasn't really a scientist. It was a philosophical question that they were trying to answer. So that was a long, long time ago. Now let's look down here the next. What's the next thing coming down here? The Greeks also, they loved trying to answer questions. They love it. And they thought their periodic table, they didn't call it a periodic table, but their table of what things are made of had 4 elements. 4. What were the 4 things that the Greeks thought everything was made of? Water, earth, air, fire. How'd you know that?
God.
Okay, good. Well, anyway, they would have thought everything was like that. Now, if you were a rock, you'd have a lot less air and a lot more earth, wouldn't you? And so the right combination of those 4 things would make every material on the earth. Well, that wasn't bad. That wasn't a bad idea. That's a good start, wasn't it? It was a good start. And then you go down here, it says during the next 2,000 years, people started studying matter. And some of them studied matter because they thought they could make money. Some people studied matter because they thought it was very godly. They thought they were going to try to discover something that God had created. Some people wanted to do it just because they wanted to answer questions. And that next 2,000 year period of time, there were these people that tried to make changes occur. They would heat this, they would cool this, they would hit it with a hammer, they would melt something. They would do everything they could, and they were called alchemists. Have you ever heard of alchemy? Mm-hmm. Now, unfortunately, alchemy in a lot of humanities texts talk about people that are kind of weird. Were there some people that were kind of weird? I don't know about the word weird, but some people thought there was a mystical or magicalness to it. When you change something from one thing to another, they thought it was kind of a magical thing, mystical. Can't really tell what kind of things are going on here. There are some people, though, that developed they knew how to change matter, and they didn't want other people to know their secrets. Have you ever had somebody who made like the best brownies or the best chocolate chip cookies, and you asked them for the recipe, and they said, well, no, that's my grandmother's recipe. You ever heard that all? And they don't want to tell you? Well, back then, the same thing there. There were people back then, some of the alchemists, they didn't want people to know how they did it, so they actually wrote in codes, and they had special names for the elements. They didn't want you to know they were talking about silver, so they made another name, or they made symbols. And there's a lot of alchemy out there that was kind of unusual. But if you read about alchemy, you'll see that they did a great deal. They developed glassware. Hey, I need this kind of glassware to do this thing I want to do, this change. And they discovered elements. They discovered how to make acids. There were a lot of things that they did. We didn't call it real chemistry back then because it wasn't really organized. But alchemists had a great deal to do with furthering chemistry. Now we get down here, and we have Robert Boyle here. And Robert Boyle is, when you take physics, you'll hear about Boyle's law, but just like a lot of scientists back in the 1800s, maybe even 1600s, a scientist didn't specialize like today. Today you go to college, biology major, then you get maybe your master's degree, maybe your PhD, and then you do biology. You see that? Back then that didn't happen. Scientists were trying to answer any question that came up. So Robert Boyle is in every physics book, but he's also in your chemistry book because he dabbled with that too. And you'll see that throughout those centuries, that these people like Faraday. Remember Faraday? Yeah. Well, I think I'll do something here with chemistry. Oh, I think electromagnetism, see? Whatever it was that they thought was interesting at the time. Anyway, one thing I highlight here is that this is where you might say modern chemistry got started, because Robert Boyle said his main contribution to science was the insistence that science should be firmly grounded in experiments. And that means an experiment you could redo, and you can actually have evidence with it. He also had, you remember the word quantitative? Yeah. He thought the experiment should be quantitative. You can actually measure something and see that it increased or decreased or whatever. Anyway, so we go on down here, and I'll probably just go to one more scientist that again might be about, well, that might be enough for today. Well, this is kind of a background of getting closer and closer to what are things made of. Remember, nobody knows like you did. If you went back in time and said, oh, don't you know about atoms? What are atoms? Don't you know about chemical reactions? What do you mean? So there are a lot of things they wouldn't have known. And we take for granted that what I'm teaching to you today, you think it happened like last night or 2 weeks ago or 2 years ago? Or no. This is a story that's maybe a 400-year story, maybe 1,000-year if you want to count the alchemist. And what we have in the book today is what we believe is true, and who knows? In 20 years, there might be something new that we haven't discovered. Now, the next part of the chapter, we've already done. The author thinks you haven't studied elements yet. You actually know all the names of the elements, is that right? You know the names. So I'm not going to spend a whole lot of time on that. But I will say that what I think is interesting is take a look at this chart right here. And this says the most abundant elements on the earth. That's in the earth's crust, oceans, and atmosphere. And what do you see there? What's number one? What is the number one leading element found on the earth?
Oxygen.
That is up there. Oxygen, and what else? So there's more oxygen, and it doesn't mean just the stuff you breathe. Like sand is silicon dioxide, SiO2. Every bead of sand, most rocks have oxygen in them. If we were to go to the moon and we need oxygen, you're not going to find it in the air because there is no air. There is no atmosphere on the moon. But could we take a rock and change it, chemically change it, and get oxygen out of the rock? Yes. All right. Anyway, silicon is all over the planet, okay? And then we have aluminum and iron, and then when you get down here, calcium, sodium. Anyway, these are the most abundant elements on the Earth's crust and the oceans. And hydrogen's up there. Where's hydrogen?
It's the last one. On the first.
Oh, there it is. Okay. And it's by mass. Unfortunately, each hydrogen atom doesn't weigh very much, so it might have more hydrogen atoms than anything else, but they don't weigh that much. Here's another one I think is interesting. What about living things? Everything I mentioned was non-living. What are the most abundant elements in living things? I said, well, I never thought about that. Well, I think Miss Founds would have done something like this. She probably would have said, what about the 4 most abundant elements found in living things? Do you remember that? Mm-hmm. And that's right here, isn't it? And when you did a unit on what kind of molecules they called organic molecules, organic means carbon compounds. Living things have carbon and hydrogen, oxygen, nitrogen. What is found in carbohydrates? Do you remember that? Carbohydrates, the most famous carbohydrate you would have known would have been C6H12O6. That's a sugar, isn't it? Sugars and starches are carbohydrates. What elements are found in carbohydrates? CHO, isn't it? Matter of fact, there's always a 2-to-1 ratio of H to O. That's what carbohydrates are, sugars and starches. What about proteins? Proteins are made of amino acids. Amino acids have what in them? They have carbon, hydrogen, oxygen, nitrogen, and not in proteins. Anyway, so they have usually this. Every once in a while you'll find a sulfur in there, but not very often. So there's your proteins. Matter of fact, that's why you need proteins, because you aren't going to get any nitrogen atoms from carbohydrates. You don't eat sugar and starch all day, you're all right, but you'll be malnourished. Just like a lot of people on the planet. You can give them bread and water, they'll be malnourished. You never did give them nitrogen atoms. They had nothing to build proteins with. That's muscle. They can't build proteins if you don't give them nitrogen atoms. You get that? Now, then we had, what's the next thing you would have known? Lipids. Did you guys do lipids?
Yeah.
Okay. Lipids have C, H, and O, but they have a really high ratio of H to O. So it might be like C20H 100O3 or something like that. All right, then the next one was they called nucleic acids. Remember that? Nucleic acids, though, are not for building. They're not for building like the other ones were. They're for information. And that's where God really shined, because he had these molecules that had information in them. Just like, I know you can say to yourself, chemicals can't have information, and then you look at your phone all day. Where's the information in your phone? I don't know. It's on the screen. What is stored in your phone? It's a bunch of ones and zeros. It's actually a bunch of ons and offs, aren't they? And it's only got 2 letters in the alphabet. And it makes all that stuff. It makes all those pictures. So you think if you only had 2 letters in the alphabet, you can do all that? What did God do with 4 letters of the alphabet? With A, T, C, and G. Could he code information to make you and you? And so what's in nucleic acids? C, H, O, and now you can say phosphorus. So anyway, notice that the list of the living things is not the same as this, isn't it? Oxygen's in both those, isn't it? That's up there, way up there. All right, so I thought that was the interesting part, the living part of the planet versus the non-living part of the planet. All right, this has to do with symbols. You know that all symbols are either one capital, one small letter, okay? We'll talk with this guy tomorrow. And what I want to do is I'd like to go to this right here. All right, so at one time, they thought that the atom was, they weren't sure what it was. So they just said, well, maybe it's a little thing. And I don't know why they thought round instead of square. I don't know. But they thought they were little balls. We don't. They didn't know. They didn't know that. They just knew they were small. And they said everything's made of atoms, and they're small. But what is an atom made of? What is an atom made of? And nobody really knew. Nobody really knew. Okay? And yet this guy named Dalton, he came up with the atomic theory saying, of all the stuff that people have done throughout history, I'm ready to tell you what we think we know about atoms today. And anyway, so he had the atomic theory, which was actually on another page. Let's see here. Here it is. Okay. Here's what he said. Here's Dalton. He says elements are made of tiny particles called atoms. Do we believe that today? Okay. Number two, all atoms of a given element are identical. Well, as far as that time period, the answer would have to be yes. We later found out that they're not all identical. Not all hydrogen atoms are identical. They have something in common with each other, but they're not all identical. Three, the atoms of a given element are different than those of another element. That's still true today. Carbon atoms are different than hydrogen atoms, aren't they? But what makes them different? What do you think makes them different? What makes a carbon atom different than a hydrogen atom? Electrons might have something to do with it. What else? Protons. Okay, maybe even neutrons, right? Okay, let's go next. He said atoms of one element can combine with atoms of other elements to form, and he got that from experimentation. He never saw it. He never saw it happen. He got his evidence showed that it must be happening. And we believe that today. Atoms are indivisible in a chemical process, meaning if you react to chemicals, you'll never destroy an atom in a chemical reaction. And we still believe that today. You okay with that? That's not bad for somebody in 1800s. That's pretty good. Yeah. So anyway, I'll go back to Dalton a little bit later. We got to the point where people thought, well, this atom is made of something. Well, something really important happened. Where I don't see, they don't have a picture. Here it is. I want you to think about this. Back then, there's this guy, his name was J.J. Thomson. And he's trying to study the atom. And think about this. I've got to find somebody who knows how to make glass. And I need to know how to make glass that when I take the air out, or most of the air, it won't break. And by the way, find the good people that make these glass, I want them to put something in the glass. I want them to put a metal disc at each end and connect it to a piece of wire. Yeah. And I want to make sure I can still take most of the air out. Okay. And then I have to, hopefully, luckily, somebody has developed a way of making electricity. You guys take that for granted. You flip on the switch and you said, it comes from somewhere. Back in the 1700s, how did you make electricity? You know, remember Ben Franklin? Hey, let's fly a kite in bad weather and well, can you depend on that? Can you control that kind of stuff? No, you get killed by it. But then somebody developed a way to make electricity in the laboratory. And they got better and better at it. And so now, this guy, he's got to take all this technology, had to be there, or else he couldn't do this experiment. He runs a lot of electricity through this disc, and then he notices there's a beam that appears, and it goes from one end to the other. And he's not sure what that is. He's not sure what it is. But he, just like a scientist, he's going to test it. So he hooks up a magnetic field, and he has a magnetic field. Let's talk about electrical fields, okay? And he makes the top end positive. So he makes this top of the field positive, this is negative. Well, what happened to the particles? Did they keep going straight? No, they seem to be attracted to what? They seem to be attracted to the positive field. So what did that tell him? These particles must have a charge to them. Which charge do you think they have? Negative. He didn't know what those were, but he said, wow. And they were later called electrons, weren't they? Can you understand what happened here? From the atom being a solid little ball, we now know the atom is made of something smaller than the atom. That stuff came from the atom. It's not the atom. It's something smaller than the atom. The atom is neutral. And the thing that came from the atom is negative. What? Where'd you come from? And then somebody says, wait, if the negative stuff can be driven off the atom, there must be something left behind that was what charge? Positive. And all of a sudden, a whole new way of thinking said, boy, the atom, if we could figure out what the atom's made of, we could make some great discoveries. And again, this took lots and lots of time. Well, anyway, we had a person who thought that the atom was what they call the plum pudding model. Did I give you a handout sheet? Take a look at the handout sheet. Look for a page in there that has pictures of atoms, the models of atoms. You see that? What is it, about 3 or 4 pages in there? Do you see like a picture and it says like Dalton? And is there one called, what's a plum pudding? Does it say plum pudding?
Yes.
Who is that?
Oh, never mind.
Is that William Thompson?
I see Thompson.
Okay, no, William Thompson had the plum pudding model, right? And he was actually, his name was Lord Kelvin, wasn't it? Ooh, that was Lord Kelvin. Anyway, so he thought it was like plum pudding. I've never been to England, but I know they still serve plum pudding there. And it's kind of like a gooey material with maybe raisins in it. So I think the atom's like that. You know, I think the plum pudding's a positive part of the atom, and the raisins are electrons. And if you do it just right, you can make those electrons jump off the atom. Yeah, that's what the atom is, plum pudding model. And then something happened which changed everything. And this guy here, his name was Rutherford, and he was from New Zealand, and he did this experiment. And I'll get into more detail of this tomorrow, but he said he had an experiment where he fired incredibly tiny bullets at atoms. And what he said is, if atoms are like plum puddings, when I fire these little positive bullets toward the atoms, every time they hit a plum pudding, they should be deflected because they're positive. But he noticed that almost 100% of the beam he sent through there went right through. And it's almost as if there was nothing there. But there was some deflecting. Here's some deflecting, and some even came back. Not very many. And he said, something is not right with that plum pudding model. He said, my experiment shows that the atom must be mostly nothing. What? Almost every one of my positive bullets went right through, as if there was nothing there. And today, that's what we think today, most of the volume of an atom is nothing. And it's incredibly, incredibly tiny, tiny part of the atom in the center, called the nucleus, is positively charged. And we believe the protons are there, don't we? And then we think the electrons are not there, but they're outside the nucleus. But this is the first time that anybody thought that the atom had a nucleus. A nucleus in the center, and the electrons not in the center. That is the first time that anybody did that. And that's still the same model we use today. So I'll get a little bit more into the scientists as we go. But I want to excite you a little bit if I can. In case you were wondering how big the atom is, let's take a look at some numbers here. Here's a typical atom, and you see where it says 10 to the minus 8 centimeters? So we think from, like that little thing you saw, from one edge of one atom to one edge of another atom, it's about 10 to the minus 8 centimeters. That's not very big, is it? Right? All right, so that's about 10 to the minus 10th meters. Wait, what's that? What's 10 to the minus 10th meters? Angstroms. Is that angstroms?
No.
Yeah. So 10 to the minus 10th meters is an angstrom. Anyway, if this is 10 to the minus 8 centimeters, how big is the nucleus? 10 to the minus 13th centimeters. Wait, I want you to think about this. How many powers of 10 smaller is the nucleus than the outside the atom? 5 powers of 10. What's that? 100,000. The diameter of the nucleus is 100,000 times smaller than the diameter of the atom. And so what is in between the nucleus and the electrons? Empty space. Empty space. And that's where you hear these articles where they talk about supermatter. super dense material. You heard that? If you could crush, if a planet's gravity could crush an atom into all of it into about the size of the nucleus, you'd have a spoonful that would weigh like 3 tons or something like that. Super matter. You heard that? Neutron star stuff. Well, that's what they're talking about, crushing the emptiness out of an atom. All right, so I wanted to show that to you to get started here. Let me watch my time. Okay, I'm sorry. You got to go. I'm sorry. I got a little carried away. All right, goodbye.